let's start to define some terms, and so that you can understand this subject about radioactive decay and the basis for radioactive dating. Every element, whether it's carbon, oxygen, hydrogen, is made up of atoms, and each of these atoms has the same unique number of electrons and protons. And the number of neutrons, however, in the nucleus of the atoms in many elements can vary. So, for example, you've got carbon-12, carbon-13 and carbon-14. The differences in those is that there are more neutrons, 2 more neutrons in carbon-14 than in carbon-12. Now, these 3 different types of carbon atoms are called isotopes. Now, some atoms in some elements have too many neutrons in their nuclei, so they become unstable. They can't hang on to them. There's not enough energy to hold all the particles together. And so some of these unstable isotopes may decay by spitting out some of the particles that are held in the nucleus, okay? And so that to reduce their size to become more stable. But when they do that, the number of particles in the nucleus has changed, so they become a different element, because each element is defined by the numbers of protons in the nucleus. So this process where the unstable atoms decay or spit out particles is called radioactive decay, because people used to use a Geiger counter or something like that to hear the clicks of the particles that were coming off, for example, off uranium. And these decaying isotopes are known as radioactive isotopes, or just radioisotopes for short. And when these radioisotopes decay, they result, the end product are stable isotopes of different elements. Okay, so you go from a parent element to a daughter element. The decaying isotopes are called parent, and the resultant stable isotopes are called daughters. Okay, the parent decays and changes to a new element, which is a daughter element. It's not that difficult, you just got the terminology to get your brain around. And so there's ones of interest to us tonight that are of interest to geologists and archaeologists. Everyone's familiar with carbon-14, which decays to nitrogen-14, and we'll talk about that more a little later on tonight. But people have heard of uranium that decays to lead, potassium that decays to argon. You might not have heard about rubidium that decays to strontium, but you've also got samarium, which is a rare earth element that decays to neodymium. And those numbers, like uranium-238, the 238 describes the size of the nucleus of that atom. And it's large, it's the common uranium atom, and it decays down to lead-206. And you're going to hear a lot about that in the next few days. So minerals, rocks, and fossils can all contain some of these parent radioisotopes and daughter isotopes, which is the basis for being able to do this radioactive dating. Well, how does it work? A rock is chemically tested for these isotopes. You get samples, you take them to a laboratory, and they measure the amounts of these isotopes. And it is assumed that if the rate of radioactive decay has remained constant at the rate we measure today in the laboratory, then you can calculate how long it has taken for the measured amount of daughter to accumulate, and that's the rock's age. Now, I've included on the screen there a little hourglass to give you the idea, because the analogy is quite simple. The sand in the top glass bowl represents the parent atoms. The sand in the bottom glass bowl represents the daughter atoms. As they fall, the parent atoms change to daughter atoms down the bottom, and the falling process is analogous to radioactive decay. Now, you can understand that if you take an hourglass like that and say it represents 1 hour's worth of sand, if you start with all the sand in the top glass bowl, within an hour it will all have fallen to the bottom. Okay? So it's quite simple. You start by turning all the glass over, so you've got all the sand in the top glass bowl, at the beginning of your timing experiment. You leave it running and you go out and start doing the laundry or cooking a meal, and you come back, you want to know how long you've been doing that task, and you notice that half the sand is up the top and half the sand is down the bottom. So how long has it taken you to do that job? Half an hour, because you know the decay rate is 1 hour. And you've still got half left at the bottom, at the top, and half left at the bottom. Half at the top and half at the bottom. So it's not that difficult. That's what the geologists do. They measure the amounts. Knowing the rate, they can calculate how long ago the process started. And this process is supposed to have started when the rock formed, so that becomes the age of the rock. It really isn't that difficult to understand. However, here's the catch. You have to make assumptions. You have to make assumptions. Because the method only works if you assume these three things are true. First of all, that assumption number one, the amounts of parent and daughter isotopes at the beginning when the rock formed must be known. In other words, the initial conditions. Now, when you started the hourglass, you tipped it up, and you had everything at the top, and then you went off and did your job. But the geologists weren't there when the rocks formed. So how do they know that there were only uranium atoms and no lead atoms? What if there were lead atoms there to begin with when the rock was formed? Unless you know the initial conditions, you don't know whether your clock really started ticking with only uranium atoms. So you have to assume that the initial conditions, even though you weren't there. Secondly, you have to assume that all the daughter atoms that you measure in the rock today have only been derived by radioactive decay in that rock from the parent atoms. In other words, it has to be a closed system. In other words, you can't have contamination. What if in the supposed millions of years, groundwater flowing through the rock added lead or washed away uranium? You'd never know for sure whether your rock has remained uncontaminated for millions and millions and millions of years. Now, you can understand it's a wide-sweeping assumption. I mean, it's like with your hourglass. Little did you know while you were out doing the laundry, your mischievous 13-year-old came and lifted up the lid and put some more sand in. He contaminated your clock. And you thought you had been going for half an hour, but actually you've been going for 40 minutes. You see what happens? If it isn't a closed system that can't be contaminated, you can't use that clock accurately. And thirdly, obviously, you have to know the rate of radioactive decay. It must have always been constant at today's measured rate. Now, the scientists have only been measuring radioactive decay for the last 100 or so years. It was only discovered just over 100 years ago. And so they've taken 100 years of measurements and assumed that those decay rates have been constant for millions and millions and billions of years. Now, that's an enormous extrapolation of 5 orders of magnitude. So none of these assumptions are actually provable because you weren't there to test the rocks in the past. The past is no longer gone. It's gone. We can't observe and measure the past or test it. So these assumptions are not even reasonable. In everyday experience, they're not even reasonable. The daughter atoms may be inherited when the rock forms. For example, in volcanic gases, you can get extra argon. Subsequent contamination is common. Now, I want you to understand that I'm not questioning the quality of the chemical analyses. If you ever visit a university laboratory where they do these measurements, the equipment is worth millions of dollars. And the sophistication is incredible. In the case of radiocarbon, they can actually count individual atoms. And they can reproduce their measurements with incredible precision. So we don't dispute the quality of the chemical analyses. But what happens is the geologist takes the analyses and interprets the numbers to calculate an age based on these assumptions. So what we're disputing is the ages and the assumptions. The need for assumption number one, however, the initial conditions, geologists have found a way to get around that by using the so-called isochron method. which we don't have time to go into details tonight because it's fairly complex. Assumption number 2 is easily discovered to be violated when contamination is detected. It's quite common to find rocks that are contaminated when they do the analyses, and so they discard those results. Not all results are ever published if they don't fit preconceived ideas about what the age of the rock should be. They put it down to contamination. However, it is insisted that assumption number 3, that is a constant decay rate, is universally true. It's supposed to be a universal condition, just like the speed of light, that they say can't be violated. Why? Because the resultant millions of years, ages, are needed for evolution to be possible, as we discussed this morning. You see, however, we're all aware that these millions of years, ages, are certainly way out of sync with the biblical time scale of only 6,000 years. So something is radically wrong if these radioactive methods give millions and billions of years when the Bible only talks about 6,000 years. But the interesting thing that I want to point out tonight, and I'll come back to this later, is often the resultant millions of years ages usually still match the relative order of the strata. In other words, rock layers down the bottom usually give older ages than rock layers up the top. And there's a reason for it, as we'll see shortly. But just hold that thought and we'll come back to it. For example, Precambrian rocks, ones down in the crystalline basement of the Grand Canyon that we'll talk about on Thursday night, usually date at older than 545 million years. And that's supposed to be the age of the Precambrian. So the question we should ask ourselves, if there's a matching of the relative order with the millions of years ages, which are highly inflated, of course, compared to the biblical timescale, we have to ask ourselves, why should radioactive decay rates have always been constant at today's measured rates? Why should that be an assumed constant? What if radioactive decay had changed in the past? If it had, and the clocks tick faster, then we couldn't use them to measure the ages of rocks. Well, I was involved in an 8-year project initiated by creationists called the Radioisotopes and Age of the Earth Project, the RATE project. And that project concluded that assumption number 3, that is, the constant decay rate assumption, is absolutely false. And I want to demonstrate that to you tonight. In this project, we discovered 5 independent lines of evidence that demonstrate that radioactive decays must have been grossly accelerated during one or more recent catastrophic geological events, especially during Noah's flood. Now, that makes sense. If we had catastrophic rock formation and other geological processes during the flood, why not catastrophic rates of radioactive decay? So if that's the case, and the clocks tick faster in the past, radioactive dating cannot be used to accurately give us the absolute millions of years ages that are claimed for the rocks. Well, let's look at these evidences. Number 1, helium in zircons. Zirconium silicate is a little mineral called zircon. And in zircon, these zircon grains, they contain uranium. They're highly radioactive. And as a result of having the uranium. And as the uranium decays, a byproduct of that decay is helium. So every uranium atom that decays actually produces 8 helium atoms as a byproduct. Now, some years ago, there were investigations into